vibrations take place in different objects, from the strings of your guitar, and even bridges vibrate when vehicles pass by on it. This happens because atoms continuously vibrate in a molecule. These vibrations or oscillations generate waves.
Vibration happens when an object repeatedly moves back and forth. As an object moves towards right and left, it is worth to note that the maximum displacement it travels is equal in both directions. Also, it covers a definite path in equal interval of time. We call this a simple harmonic motion. Some examples of simple harmonic motions in real life are the motion of the hand of the clock, the motion of the wheels, and the motion of a pendulum.
Waves that need a medium through which they can travel is known as mechanical waves. Mechanical waves have two classifications, and these depend on how the motion of the individual particles of the medium is related to the motion of the wave itself.
A transverse wave is present if waves in which the medium moves at right angles to the direction of the wave. Another is when waves in which the medium moves back and forth in the same direction as the wave. We call this as compressional or longitudinal waves. When the end of the spring is pushed and pulled, a series of compressions and expansions occur. Compressions, or the areas where coils are close together, and expansions, or the areas where coils are far apart, are equivalent to the crest and troughs of a transverse wave. Transverse waves travel through a medium whose particles are attached to one another. Gas particles are widely separated, making transverse waves unable to travel through them. A longitudinal wave causes particles of a gas to move closer together or farther apart, making gas a medium for it.
Both transverse and longitudinal waves can travel through a solid, since the particles of solids can vibrate about their relatively fixed positions in any direction.
Surface waves possess both transverse and longitudinal properties. This makes the particles in the medium move horizontally and vertically as the waves moves across the surface. Water waves are an example of surface waves.
Now let's talk about wave characteristics. When we talk about wavelength, this refers to the distance between one point on a wave and the exact same place on the next wave. Wavelength can be represented by the symbol. We call the symbol as lambda. In this illustration, we can see that from this point up to this point, it is a wavelength. Another, at the bottom, we can see that from this point up to this point, it is also a wavelength. Now, the highest point in a wave is what we call the crest, while the lowest point in a wave is what we call the trough. So from crest to crest, it is a wavelength, and from trough to trough, that is also a wavelength. Now let's talk about the amplitude. Amplitude is represented by small letter a. It refers to how far the medium moves from rest position or from the midpoint of the wave, where it is when not moving. Remember that for transverse waves, the highest point is the crest and the lowest point is the trough, just like what I have said to you a while ago. In this illustration, we can see how an amplitude looks like in a wave. So from this midpoint up to this point, that is the value of its amplitude. Next is the frequency, represented by lowercase letter f. Frequency refers to the number of crests or waves that pass a fixed point per second and is measured in hertz. In symbols, we have capital letter H and the lowercase letter z. Next is period, which is represented by uppercase letter T. It is the time in seconds it takes a wave to travel, a distance equal to a wavelength. It is reciprocal of frequency, so mathematically, we can express this as T is equal to 1 all over F, or F is equal to 1 all over T. Let's take a look at this example. Let's say that this is bulb A and this is bulb B. And let's see how they flash. Bulb A, as we can see, bulb A completes one complete wave cycle in every 1 second. Therefore, its period, or t, is equal to 1 second, while its frequency is equal to 1 flash all over 1 second is equal to 1 hertz. On the other hand, let's check out bulb B. As we can observe, bulb B flashes slower compared to bulb A, and bulb B completes one complete wave cycle every 2 seconds, or bulb B flashes every 2 seconds. Therefore, its period is equal to 2 seconds, and its frequency is equal to 1 flash all over 2 seconds, that is equal to 0.5 hertz. Another, we have the wave speed. Wave speed depends on the medium in which the wave is traveling. It varies in solids, liquids, and gases. Mathematically, we can express this as V is equal to lambda all over t, where V represents the wave speed, lambda is our wavelength, and t represents our period. We can also write our wave velocity formula in another way. Since t is equal to 1 all over f, that means that we can write velocity is equal to lambda all over f. Let us have a sample problem. A wave is formed by moving a string up and down. Crests are measured every 0.3 meters, and a period of 0.25 seconds is observed. Calculate the frequency and velocity of the wave. In this illustration, we can see that an incident pulse that is moving towards the right gives us a reflected pulse that is moving towards the left but in different orientation. Step number 1, the goal of this problem is to calculate the velocity of the wave. To accomplish this, we first determine the frequency of the wave. In order to do that, we have to use our formula for finding frequency. F is equal to 1 all over t. That is equal to 1 all over 0.25. That gives us the answer 4 hertz. Step number 2. To calculate the velocity, we use the equation velocity is equals to frequency multiplied by the wavelength. Since we have already the value of the frequency, which is equal to 4 hertz, we are just going to multiply it by 0.3. Multiplying 4 to 0.3 will give us the answer for velocity, which is equal to 1.2 meters per second. It can be shown that the velocity of the wave increases with the tension in a string or spring. The reflection of a one-dimensional transverse pulse can be observed when a string is tied at one end. It will be observed that the pulse returns inverted from its original phase orientation. If transverse waves are sent along a string tied at both ends, and if the frequency is timed correctly, then a standing waves occurs as the incoming waves mix, or the superpose, with the inverted reflected waves. The resultant wave will appear to be standing in one place, only showing an up and down motion. Points along the wave where there is no appreciable motion are called nodes. The maximum displacement points are called the antinodes. Nodes appear every half wavelength in a standing wave. Notice that if the frequency is increased or decreased, the number of nodes would increase or decrease also. Let's have another sample problem. A string is stretched to a distance of 5 meters and held under constant tension. A transverse pulse is generated and takes 1.8 seconds to travel from one end to another, and then back again. What is the velocity of the pulse? Second, standing waves are now generated and nodes are observed every 25 centimeters. What is the wavelength of the wave? And third, based on your answers to parts A and B, determine the frequency of the wave. Assume the tension stays constant. Step number 1. The velocity of the pulse is simply the distance divided by the time to go one length down the spring. We are given the round trip time. V is equals to distance all over time. Therefore, that is equal to 5 meters all over 0.9 seconds, which gives us 5.55 meters per second. Step number 2. Because the conditions of the medium are constant tensions, we can produce standing waves. The nodes appear every half wavelength. It is observed that the nodes appear every 25 centimeters, hence, lambda is equals to 50 centimeters or 0.50 meters. Step number 3. To find the frequency, we note that velocity of any wave in the spring will be the same since the conditions are constant. This means that we can use the equation V is equals to F multiplied by lambda. We are just going to plug in the value that we have. V is equal to 5.55 meters per second. That is equal to frequency multiplied by 0.50 meters. Divide both sides by 0.50 meters to find the frequency, and that will give us the final answer for frequency, which is equal to 11.1 Hz. This concept of mixing waves, called superposition, leads to the concept of interference. If we have one-dimensional waves in a stretched string or spring, then two pulses, let us say, oriented upward with amplitudes A and B respectively, moving towards each other will constructively interfere when they meet. That is, at the point that they meet, the material will be pushed upward and will produce a resultant pulse with an amplitude equal to A plus B. The pulses will then continue onward undiminished. Illustration shows that pulse A and pulse B will be going to meet at a specific point. We can observe that pulse A and pulse B are both oriented upwards. Therefore, resultant pulse will be equal to A plus B, thus giving us a bigger pulse. After that, both pulses A and B will continue to move on their direction undiminished. If the phase orientation on pulse A is reversed upside down, then when the pulse meet at point P, they interfere destructively, A minus B, before continuing onward. Assuming equal amplitudes, opposite phases, then A minus B is equal to 0. As we can observe, pulse A and pulse B are in different orientation. Therefore, we can say that we will be having a destructive interference. Once they met at a specific point or location, we will be having a flat line like this. If we generate two-dimensional waves, let's say in a water tank, then we can see more wave properties. A point will generate wave fronts that are circular. If we have a straight wave generator, then the wave fronts will be known as plane parallel or just straight wave fronts. If plane waves are incident on a barrier at some angle, measured to a normal line drawn perpendicular to the barrier, then the waves will be reflected back at an angle equal to an angle of incidence. This is known as the law of reflection. When a wave hits a barrier, the wave will be then reflected back, and as we can notice, the angle of the reflected wave is just equal to the angle of the incident wave. If the plane waves are incident on the edge of a barrier or a small opening or aperture, then the wave will diffract around the barrier. The explanation of this wave behavior is due to Christian Huygens, who stated that when plane waves are incident on a small opening, the opening acts like a point source and produces circular wavefronts. It is important to remember that interference and diffraction are phenomena only characteristic of waves, not particles. This is how diffraction of plane waves will look like. If the barrier have a small opening or an aperture, the waves will act just like this. The interference of two-dimensional waves can be demonstrated by a ripple in a water tank and modeled using a series of concentric circles. If two-point sources produce circular waves, then where the crest, which is the outer edge of the circle, overlap, we have regions of constructive interference, where crest and trough overlap midway. There will be regions of destructive interference.
The floating toy boat, which was initially at rest, is put into motion by the water waves. This indicates that the waves provided energy for the boat in order to make it move. Based on this, we can say that the waves are energy carriers. As the wave travels through the medium, it transmits vibrational energy from one particle to another particle of the medium. Energy is transferred by the simple harmonic motion of the particles.
Thank you very much for watching.
We hope that you learned.
See you on our next topic. Bye!